b1. So the instantaneous velocity of the particle will be given as limit delta t tends to 0 delta r by delta t, where delta r is the vector between point a1 and b1. This is our delta r. So this expression is nothing but the derivative of displacement vector with respect to time. So this is our instantaneous velocity. Now let's move on to instantaneous speed. Instantaneous speed is the rate at which the distance is traveled at a particular instant. It's the same as the average speed of an object in a very small duration of time around that instant. So suppose if an object travels a distance of delta L in a very small duration of time delta t, then the instantaneous speed can be defined as limit of delta L by delta t, where delta t tends to 0, and we know that it's equal to dl by dt. Now the distance traveled by an object in very small duration of time will be very small, and even if the object's path is along a curve, for very small length this curve can be approximated to a straight line segment. So instantaneous speed will be same as the magnitude of instantaneous velocity. Now let's see how this is possible. So suppose an object travels from point A to point B along some path, and we need to find out the instantaneous speed at some instant t. So let that at instant t the object is at point A1. So to find the instantaneous speed at this instant, what we'll do is we'll take the object's position at point t plus delta t, and let's suppose that at this instant the object is at b1. So as you can see that if we keep delta t very small, then the length of a1 and b1 would be very small, and even if it's on a curve, we can approximate the segment a1 b1 as a straight line segment. So in this case, the magnitude of displacement, that is straight line between a1 and b1, and the magnitude of distance, that is length of the curve between a1 and b1, will be approximately equal, because we have made delta t very small, and so the segment a1 and b1 can be approximated as straight line. So that's why instantaneous speed will be equal to instantaneous velocity. In fact, it will be equal to the magnitude of instantaneous velocity. Now let's define average acceleration. Average acceleration is defined as the change in velocity divided by the time interval in which the change has occurred. So if v final is the velocity at the end of the interval and v initial is the velocity at the start of the interval, we can define average acceleration as vf minus vi by delta t. Similarly, we can define instantaneous acceleration as we had defined instantaneous velocity and instantaneous speed. So instantaneous acceleration can be defined as the rate of change in velocity. So we can define instantaneous acceleration, that is a, as limit of delta v by delta t, where delta t tends to 0, and it is equal to dv by dt, and here v is the velocity of the object. Now we can summarize all the definitions that we have discussed so far. So let's see all those definitions one by one. So average velocity was equal to s by t, where s is your displacement and t was the time interval. Instantaneous velocity was equal to ds by dt, where again s is your displacement. Instantaneous acceleration is equal to dv by dt, and as we have already seen that v is equal to ds by dt, so a will be equal to d by dt of ds by dt, which is d square s by dt square. So this is one more formula for instantaneous acceleration. Also we can write dv by dt as dv by ds into ds by dt, and we know that ds by dt is nothing but v. So acceleration can also be defined as v into dv by ds. Now average acceleration was v final minus v initial by t, where v final is the final velocity, v initial is the initial velocity, and t is the time interval. Now let's find out the various equations of motion. A complete description of the motion of particle can be obtained if the mathematical dependence of its position x at any given time t is known. That is, if we know the relationship x is equal to ft, then we can very well describe the complete motion of particle. So now let's find out the relationship between velocity and acceleration when acceleration is constant. We are assuming that we know the relationship x is equal to ft. So since we already know how x is dependent on time, that is, we know the relationship x is equal to ft. So from here we can define velocity, which is v, as dx by dt should be equal to f dash t. So now the time dependence of velocity is also known, and it is equal to f dash t. Now we know that acceleration is nothing but dv by dt, or we can write dv is equal to a dt. Now since the acceleration is constant, that is, it is not dependent on time, we can integrate the left hand side and right hand side of this equation. Now suppose at time t is equal to 0, the velocity of the particle is u, and at time t is equal to t, or at any given time, the velocity of particle is v. So after integrating, we get v minus u is equal to a into t minus 0, or at. So v is equal to u plus at. So this means that velocity at any given time v will be equal to initial velocity plus at. Now let's find out the relationship between the position of particle, its initial velocity, and its acceleration. So here again the acceleration is constant, and the time dependence of position of particle is known. So we know that velocity at any given instant can be written as v is equal to dx by dt. After rearranging this equation, we can write dx is equal to v dt. Now we have already derived that v is nothing but u plus at, where u is the initial velocity. So we can replace v here. So we have now dx is equal to u plus at into dt. So we can integrate both the sides of this equation. So suppose at time t is equal to 0, the position is x0, and at time t is equal to t, the position is x. So from here we can get x minus x0 is equal to ut plus half at square. Now we'll find out the relationship between acceleration, the initial velocity, the final velocity, and the position of particle. So as we know, the acceleration is given as a is equal to dv by dt, which we can write as dv by dx into dx by dt. Now dx by dt is nothing but v, that is velocity. So acceleration is v into dv by dx. So here we have a is equal to v into dv by dx, or v dv will be equal to a dx. Now again we can integrate this equation. So suppose when the velocity was u, that is initially, the position vector of the particle was x naught, and after some time when the position vector becomes x, the velocity becomes v. So after integrating, as you can see, we get v square minus u square by 2 equal to a into x minus x naught. So finally we get v square is equal to u square plus 2a into x minus x naught. So replacing x minus x naught with s, we get v square is equal to u square plus 2as. Now we'll see how average velocity is related with initial and final velocity. So we know that average velocity is defined as s by t, where s is the distance traveled in time interval t. Now just now we have derived that s is nothing but ut plus half at square. So average velocity would be ut plus half at square by t. Now this can be written as first we can take t common in the numerator, so we'll get u plus half at by t. We can cancel out t here, so we are left with 2u plus at by 2, which we have written here. So average velocity is 2u plus at by 2. Now 2u can be written as u plus at. So average velocity is u plus at, and u plus at is nothing but v. So finally we can get a relationship, that is average velocity is equal to v plus u by 2, where v is the final velocity and u is the initial velocity. Now we will find out what is the distance traveled by a particle in nth second. So suppose we have a particle with initial velocity u and traveling with constant acceleration a. So suppose the particle starts from point A, and at the end of n minus 1th second, the particle is at point B1, and after the end of the nth second, the particle is at point B2. So this is at n minus 1th second, and this is at nth second. So in the nth second, the distance traveled by the particle is nothing but b1 b2. So this can be written as Sn, that is the distance traveled by the particle in n second, minus Sn minus 1, which is nothing but the distance traveled by the particle in n minus 1 second. So we can get the distance traveled in nth second as Sn minus 1. So now we can replace Sn with un plus half an square, where n is the